Suppose you have a graph and you want to know how to draw it. To make it easier to understand the picture, it would be nice if the edges don't cross. Can you draw the graph so that the edges don't cross? These kinds of graphs are called planar graphs. A simple but interesting question is, what kinds of graphs are planar? An answer could give you some insight into how to design graphs so that the edges don't have to cross. Let's try to find some examples of graphs that are non-planar. Obviously, if a graph contains one of these, it is also non-planar. How could adding more edges and vertices help make it easier to draw the hard bits? Let's just start adding some vertices and edges. Since the edges are the reason a graph would be non-planar, because they intersect, it makes sense that we should try to draw as many edges as possible to make the graph non-planar. This graph seems hard to draw. The last edge always seems to have to cross an existing edge. This graph is called K5, and we'll save it for later. When constructing K5, we relied a lot on triangles. What if we tried to make a non-planar graph with no triangles? It seems like this graph is non-planar. Again, the last edge seems forced to cross an existing one. This graph is called K33. You might be familiar with it through the utilities puzzle, where you have to connect 3 houses to each of 3 utilities without crossing the lines. Now, a really interesting fact is that these are really the only 2 hard graphs. In fact, every graph that can't be drawn in the plane contains one of these 2 graphs. And obviously, if a graph contains one of these problematic patterns, which we will show are non-planar, the whole graph is non-planar. Adding more stuff to the graph isn't going to help it become planar because you still need to deal with the fact that the edges of the bad graph are crossing. This fact is called Kuratowski's theorem, and it is a really cool fact about graphs. Think about it. Together with just drawing the graph in a planar way, it was a perfectly constructive way to decide if any graph is planar. Just either show a way to draw the graph in the plane, or show that there is a K5 or K33 in the graph. It also gives some perfectly local insight into how to design a graph so that it is planar. But wait, you might ask, sure, if I split an edge into 2 edges joined by a vertex, it doesn't make the graph planar. Moving around the 2 edges joined by the vertex is just like moving around the combined edge. But yet, it doesn't contain one of the bad subgraphs, according to the usual definition of subgraph. And you were right. That's why Kuratowski's theorem actually deals with subdivisions of the K5 and K33, the graphs you get if you divide the edges of the bad subgraphs into pieces. So Kuratowski's theorem states that the graph is nonplanar if and only if it contains a subdivision of K5 or K33. We are going to try to prove it in this video. But first, it will be helpful to understand why K5 and K33 are non-planar. What exactly goes wrong when we try to draw K5? Well, we can draw most of the edges, but when we try to draw the last edge, we're stuck. Why exactly? Well, look at the regions that are formed by the edges, or in the proper terminology, faces. After we draw 9 of the 10 edges, we're left with 6 faces, each of which is a triangle, meaning they're bordered by 3 edges each. Why 6? Well, we know that there are 9 edges, and each edge has 2 faces it borders. That is 18 edge face touches in total. We know that each face borders 3 edges, so that is 3 edge face touches per face. 18 edge face touches divided by 3 edge face touches per face is 6 faces. The advantage of thinking about faces like this is that we know that the last edge must lie entirely within one of these faces. If it passed through 2 of the faces, we know we would have to cross an edge somewhere. Notice how the edge must leave this vertex in one of these 3 faces. But it also must come to the second vertex in one of these 3 faces. But notice how those faces are different. So since the last edge can't leave one vertex in one face and come to the second vertex in a different face, we know that the last edge must cross an edge somewhere. So therefore, K5 is nonplanar. Let's try to generalize what we did to show that K5 is nonplanar. How do we know that the faces surrounding the final 2 target vertices should be different? It's not really obvious why that should be so. Sure, having six faces at the final step makes it possible, but how do we even know that there will be six faces at the final step? Let's start from the beginning, with just one vertex and one face, the whole of space. What can happen when we add an edge? Well, we can't actually add an edge yet, because there isn't a second vertex for it to attach to, but we can add an edge in also the vertex on the other end of it. We can also add an edge between two vertices that already existed, but didn't have an edge between them yet. What specifically happens in each case? In the first case, we get a new edge and a vertex. What happens to the faces? Nothing, because the edge can't divide the face it cuts through, because it ends early at a new vertex. What about in the second case? We don't get a new vertex, but we do get a new edge, and since the edge cuts all the way through the face it's in, we get a new face too, from the face being divided in two. So we start with one vertex and one face, and as we build the graph one edge at a time, we either add an edge and a vertex or add an edge and a face. From this we can construct an interesting invariant, number of vertices minus number of edges plus number of faces, or v minus e plus f, which stays constant no matter what operations we do. And since this number equals 2 at the start of the building process, for one vertex and one face and no edges, we know it must equal 2 for any planar graph. This is called Euler's identity and is a fundamental number in planar graphs. What about for non-planar graphs? Well, they're a bit weird because the face might have two edges that meet where there's not actually a vertex, because that is where a crossing is. So we'll just say that if a graph does not or cannot follow Euler's identity, then it is non-planar. How can we use this fact to show that K5 is non-planar? Well, if we can show that K5 violates Euler's identity, then we know it must be non-planar, because all planar graphs satisfy it. Suppose K5 was planar. Then we know that V equals 5 and E equals 10, because K5 has 5 vertices and 10 edges. Using Euler's identity, we know that F equals 7, because F equals 7 is the number that satisfies V minus E plus F equals 2, Euler's identity. Can we actually get the 7 faces we need? Well, each face has at least 3 edges, since there are no cycles of length 2 in K5. Also, there are 10 edges in K5, so they give 20 edge-face touches. Since there are 3 edge-face touches per face and 20 edge-face touches total, there are at most 20 divided by 3 faces in K5. Since that is less than 7, that is a contradiction. Therefore, we know that K5 is non-planar. How did we just prove that? We investigated how we can build planar graphs one edge at a time. Since we know that every time we add an edge, we either add a vertex or a face, we determined that the quantity v minus e plus f is constant and 2. We used that fact to calculate how many faces a planar drawing of K5 must have and compared it to how many faces it could actually have. Since the edges of K5 did not allow enough faces to be built using the structure of K5, we determined that K5 is non-planar. Something may have confused you. I said that there were not enough edges to allow enough faces to be constructed in K5. However, edges hurt planarity. They make it harder to draw the graph because they get in the way. However, adding edges also increases E, which forces F to increase, making it harder to achieve the necessary faces. How exactly? Well, Euler's formula says that the number of faces is 2 plus E minus V by simple algebra. How many faces can we construct? Well, each face has at least 3 edges, so it uses 3 edge face touchings, and each edge contributes to 2 edge face touchings. That means that the number of faces is at most 2/3 E. Why at most? Because a face with more edges uses up more edge face touchings. Then 2/3 E, the number of faces we can possibly construct, must be at least 2 plus E minus V, the number of faces demanded by Euler's formula. Transforming this, we get V minus E thirds is at least 2, or 3V minus E is at least 6. This is a common formula for quickly checking whether a graph is planar. For example, for K5, V equals 5 and E equals 10, so 3V minus E is 5, which is too small, corresponding to the fact that K5 is non-planar. However, if we remove an edge, we get v equals 5, e equals 9, and 3v minus e is now 6, which is large enough, corresponding to the fact that we succeeded in drawing k5 except for the last edge. So is k33 planar? We can try using our new formula. For k33, v equals 6, e equals 9, and 3v minus e is 9, which is plenty large enough. But it seems like k33 is non-planar. What went wrong? Euler's formula says that we need 5 faces, and from counting edge face touchings, it seems like we should be able to form 6 faces. In fact, there are plenty of planar graphs with 6 vertices and 9 edges. But remember, in that rule, we assumed that all the faces were triangles. But K33 has no triangles. You can clearly see it has no triangles because all cycles are even. You can only go from a top vertex to a bottom vertex, and from a bottom vertex to a top vertex. So to get back to where you started, you need to take an even number of edges. So if we go back to our estimation about the number of faces we can make in K33, but take into account that the smallest face is one with 4 edges, we find that we can only make 9 divided by 4 times 2 equals 4.5 faces, which is less than the 5 that are required. So despite K33 succeeding in the common test of planarity, it is non-planar. We just needed to take into account the structure of K33. So now we have proved the first part of Kuratowski's theorem. Remember, Kuratowski's theorem says that a graph is non-planar if and only if it contains a subdivision of K5 or a subdivision of K33. And since we now showed that K5 and K33 are non-planar, their subdivisions in all graphs that contain them are obviously non-planar. Now we just need to show that every non-planar graph contains one of those subdivisions. We can try to prove this using proof by contradiction, and can make some simplifying assumptions to make it easier to form a contradiction. For instance, we can demand that the graph we're studying is the minimal non-planar graph with no K5 or K33, because if there was a counterexample, that is, a non-planar graph that did not have a K5 or K33, there must be a smallest one. Here, smallest means that if you remove any edge or remove any vertex, you get a graph that is either planar or has a K5 or K33. The second option doesn't make any sense, because how could a subgraph have a K5 or a K33 without the whole graph having one? So we're looking for a graph that is non-planar, has no K5 or K3, and where all of its subgraphs are planar. And we can call that graph G. In fact, we can choose G such that any graph that has fewer edges, not necessarily a subgraph, is either planar or has a K5 or K33. The contradiction could come by showing that the graph actually does have a K5 or K33. How do we show it has a K5 or K33?
Convention break! In this video, a dashed line will stand for a path between two vertices. And additionally, two dashed lines will represent two distinct paths, paths that don't share any vertices in the middle.
One place to start is by noticing how both K5 and K33 have two vertices that are joined by 3 distinct paths. It will actually be pretty easy to show that G has a K5 or K33 once we show it has this configuration, specifically one where one of the paths is a single edge. How can we show that G has this pattern? Well, if we call these two vertices U and V, we can show that there is an edge between U and V, and also if we remove that edge, then there is a cycle going between U and V. We can do this using a notion of connectedness. We say that a graph is k-connected if you need to delete at least k vertices in order to disconnect the graph. A graph with a higher k is in a sense more robust and interconnected. For example, K5 is 1-connected because it is connected in the normal sense. It is also 2-connected. We can see this because between any two vertices, there are 2 paths, and we need to destroy both paths in order to separate the 2 vertices. The important part is that the paths don't share any vertices except for the ends, so we can't destroy both with a single vertex cut. Is the reverse true? If a graph is too connected, is there always two distinct paths between any two vertices? This would in fact mean that there is a cycle going between any two vertices, which is part of what we want to show is in G, our hypothetical nonplanar graph with no k5 or k through 3. Let's try to prove it. If we call the two vertices u and v, we want to show that if their graph is too connected, then there are two distinct paths going between u and v. What if u and v were connected by a single edge? Well, the meaning of too connected is that removing a single vertex does not disconnect the graph. And since removing a vertex also removes all of its edges, surely removing just an edge does not disconnect the graph either. So if we remove the edge uv, there must be another path that connects them. What if u and v were farther apart? Let's use induction on how far apart they are, called unsurprisingly, their distance. In the previous case, where u and v were neighbors, their distance is the smallest possible, only 1. Since u and v are connected somehow, there is some vertex z that lies on the path connecting them. And we can say that z is 1 away from v. Then our induction hypothesis says that u and z are connected by two distinct paths, since the length uz is less than the length uv. But those paths won't do for connecting u and v, because they both contain the vertex z. However, there's another path connecting u and v that does not contain z. How do we know? Because otherwise we could delete the vertex z, and that would disconnect u and v. It might seem like we have two distinct paths, the top one and either of the ones containing z. However, the top path might intersect either of the z paths, in which case they would not be distinct. However, if they do share some vertices, there would have to be some shared vertex that is closest to v, and this forms the two distinct paths, like this. So now we know that if a graph is too connected, between any two vertices, there are two paths that connect them, and importantly, those paths don't share any vertices. How does this help? Well, that means that between any two vertices, there is a cycle connecting them. And that is part of the structure we wanted to show that G has. So now we need to show that from G, if we remove an edge uv, the resulting graph is still two connected. And we can show this by showing that G is 3 connected. Why? Because G being 3 connected means it takes 3 vertex removals to disconnect the graph. So if we remove only one vertex, it leaves the graph 2 connected. And surely if removing a vertex and all of its edges leaves the graph 2 connected, removing just an edge also leaves the graph 2 connected. So now we need to show that G, the minimal nonplanar graph with no k5 or k33, is 3 connected. We can easily show that G can't only be 1 connected. That would mean that there is a vertex where we can remove it and disconnect the graph into 2 pieces. Why? Well, each of the 2 pieces is a subgraph of G, and since G is the minimal graph of its kind, it means that each of the subgraphs is either planar or has a k5 or k33. The second option makes no sense. How could a subgraph have a k5 or k33 when the whole graph doesn't? So therefore, each of the small graphs is planar, and we can draw it in a planar way. In fact, if we add on the vertex we removed to both of them, we still get a planar graph, because they are still subgraphs of G. Now importantly, we can put the vertex on the outside. Why? Well, we can put it somewhere, because the graph is planar. And we can imagine expanding the region the vertex is adjacent to, while flipping the rest of the graph inside out.
You can also think about slowly moving the vertex to the outside while flipping all the edges that get in the way to the other side of the graph.
This is a bit weird, so make sure it makes sense to you. Now anyway, the vertex on both of the subgraphs are on the outside, and we can merge them while keeping the graphs planar. So now we have a planar embedding of G, which by assumption is impossible. So since we have a contradiction, G must be at least 2 connected. Does G G have to be 3 connected? Say it was only 2 connected, so we could remove only 2 vertices to disconnect the graph. Say we can remove these 2 vertices. It might split the graph into many components, but I will assume it's only split into 2 for sake of illustration. The argument is the same. Now, onto each of the components add x and y back, along with the edge xy. What if all the components were planar? Then we can use the same inversion trick we did before to bring the edge xy onto the outside of each of the components. Then we can merge them together to get a planar drawing of either G or G plus the edge xy if it didn't exist before. But that would mean that G is planar, which is a contradiction. So we know that at least one of the components must be non-planar. But aren't the components subgraphs of G? Well, not necessarily, because they include the edge xy, which might not exist in G. That is why we assume that not only is G the minimal non-planar graph with no k5 or k33, but also that it is the one with the least possible edges. That means that this component must have a k5 or a k33. The only way for G to avoid this subgraph is if it did not include the edge xy. So now we can remove the edge xy from each of the components, merge them together along x and y to get G. But now G has a k5 or a k33. Can you see where? The edge xy in the non-planar component has been replaced by a path going around the other component. Since that is a contradiction, we know that G must be 3 connected. Why did we just do that? Because now we know that we can remove any edge from G, say the one between U and V, and the resulting graph will be 2 connected. Because if we were to remove a vertex from G, we would get a 2 connected graph. Removing a vertex is more powerful than removing an edge. Well, actually not quite. We have to show that if we were to remove a vertex from G, say U, and then add it back in, but without the edge UV, that U would be sufficiently connected to the rest of the graph without using the edge UV. But that's not too difficult to prove, but this video is already plenty long. So consider an exercise to prove that a 3 connected graph minus an edge is 2 connected. Anyway, G minus UV being 2 connected means that there's a cycle going through U and V, but not including the edge UV. It might not seem like it, but the proof is actually pretty easy from here. What are we trying to prove now? We're trying to prove that G can actually not exist. One way to prove that is to prove that any non-planar graph with this configuration must contain a k5 or k33, because that means that G has a k5 or k33, contrary to the assumption. So does G have one of these subgraphs? Remember that we assumed that G is minimal, so that any smaller graph, including its subgraphs, is either planar or has a k5 or k33. This means that we can remove any edge from G, including the one between U and V, and get a planar graph, since it obviously doesn't contain a k5 or k33 because G doesn't. Since the graph is planar, it makes sense to talk about drawing it in a planar way. In fact, we can declare that this cycle, C, is the fullest possible cycle that goes through U and V, and that it has the most possible edges inside of it. What do we know about this graph? We have to keep in mind our assumption that G is non-planar, but also that this graph is planar and that C is the largest possible cycle. What happens on the outside of the cycle? Say there was some connected structure on the outside of the cycle, called an exterior bridge. By connected, we mean any 2 points on the bridge can be connected by a path that does not include any of the vertices on the cycle. The bridge is connected by itself. Well, what if the bridge was connected to the cycle in only 1 point? Then we can remove that point and disconnect the bridge from the cycle. But that's not allowed because we know that the graph is 2 connected. What if the bridge connected to the cycle in more than 2 points? Well, then we actually have this fuller cycle. This cycle includes all the edges that were inside of C, plus some that were on C. But remember that we assume that C is the fullest possible cycle, meaning it has the most possible edges inside of it. So that's not allowed. Importantly, we know that this cycle goes through U and V as required, because since the bridge connects to the cycle in at least 3 points, there must be at least 2 points that are on the same arc between U and V, where U and V themselves are included in both arcs. This also applies if the bridge connects to the cycle in only 2 points, but those 2 points were on the same arc between U and V. So we know that any exterior bridge must connect to C in exactly 2 points, and those 2 points must be skew to U and V, meaning they are on opposite arcs between U and V and not at U and V themselves. How big can the bridge be? Well, we know it's connected to the cycle in only 2 points, so what if we delete those 2 points to disconnect the bridge from the cycle? This disconnects the graph, except if the bridge didn't actually have any vertices on it. But isn't this fine because we only know that the graph is 2 connected? Well, adding in the edge UV doesn't actually help connect the bridge to the cycle, but it is supposed to make the graph 3 connected, which is contrary to those 2 vertices disconnecting the graph. So any exterior bridge is actually just an edge that connects 2 points on opposite arcs of U and V. There can actually be as many of these as you want, but there has to be at least one. Remember, G is nonplanar once we add back in UV. We have to block it somehow. We need to block it both on the inside and the outside of the cycle, and the only way to block it on the outside is by using one of these exterior bridges. Let's update our picture of G. What happens on the inside of the cycle? The exterior edge does a good job of blocking UV from using the outside, but we need some way to block it on the inside. Some interior structure, also a bridge. We know that this bridge must intersect the cycle on points on either side of U and V. Why? Because otherwise the edge UV could closely follow the other arc and make it to the other vertex. In the proper terminology, we say that the interior bridge overlaps U and V. It's not skew anymore because there could be additional vertices that share arcs with those two. Another subtle fact, the interior bridge must also overlap the exterior edge. Why? Because otherwise we could flip the interior structure to the outside. There would be no reason why it would have to intersect the exterior edge because it does not overlap. And now we can easily draw the edge UV because the inside is completely clear. So in summary, we know that whatever kind of interior structure is inside C, it must intersect C in points on either side of U and V and points on either side of x1 and x2, the points of intersection of the exterior edge with the cycle. It might not seem like it, but we're actually close to proving the theorem. It's just simple casework from here. Remember that we are trying to get a contradiction to the fact that G is the minimal nonplanar graph with no K5 or K33. The contradiction could come by showing that G actually does have a K5 or a K33. So where are those subgraphs? Well, where could the connection points of the interior structure be? Remember that the interior structure must have connection points on either side of U and V and connection points on either side of x1 and x2, which themselves are the connection points of the exterior edge with the cycle. And remember that x1 and x2 are on different sides of U and V. If we arrange those 4 points around the cycle, we see that there are essentially 8 different locations we have to consider when placing the interior connection points in any of the 4 zones or directly on the 4 important points, U, V, x1, or x2. By symmetry, all the zones are basically the same. So say there was a point here in the red zone. then there must also be a point somewhere in the right half, either in the green zone or the blue zone or on their border, and also a point in the bottom half, either in the yellow zone or the blue zone or on their border. What if the points were the same, so there was actually a single point in the blue zone? Then there would actually be a K33. Can you see where? There it is. Remember that some of the lines may be paths instead of single edges, but that doesn't matter because Kuratowski's theorem allows us to deal with subdivision of K5 or K33. So in this case, G actually contained a K33 after all. Let's call this case 1. What if the right half point was at the special point x2? We still haven't taken care of the bottom half point, so where would that go? If it was in the blue zone, that would just be our case 1 configuration again. What if it was at the special point V? It doesn't look like we have any of the forbidden subgraphs. However, now we have 3 points of connection between the interior bridge and the cycle. This means that there must be some interior point that all 3 connection points attach to. If there wasn't, the bridge would actually be disconnected. Using that point, we can actually label the graph like this. So it is in fact a K33. We can call this case 2. And in fact, we can reduce this case 2 to case 1 by removing this path. Now what if the bottom half point was in the yellow zone? Again, it doesn't look like we have any of the forbidden subgraphs, but we can remember that there must be some interior point that all 3 connection points attach to. Using that attachment point, we can see that we can label the graph like this. We can call this case 3. And in fact, we can reduce this case 3 to case 2 by moving these 2 points together. We can do this because only one of the paths that went to that house had to go through the edge we contracted. And we can reduce our case 2 to case 1 to get something that is obviously a K33. Now what if the right half point was in the green zone? Where would the bottom half point be? It could be in the blue or yellow zones, but that would create another case 1 configuration, or it could be at the special bottom point V, which would create another case 3 configuration. Anyway, there must be a K33. Are we done? You might have realized we have missed some case because we haven't used K5 yet. And indeed, we've missed the case where all of the connection points for the interior bridge are at the important points U, V, x1, and x2. So what if they all were? Well, then we would have to use all 4 of the important points, or else we would miss out on some hemisphere of the cycle. Now that we have 4 connection points, we don't actually have to have just one meeting point in the middle. We could have 2. What if there was just one meeting point? Well, then there would actually be a K5 in the graph. You can see that each of the 5 vertices connects to each of the 4 others. What if there were 2 meeting points? Well, then we will actually have a K33. We can label it like this. And in fact, we can reduce this to case 2 if we delete this path. Are we done? Yes, that is all the cases. And in each case, there is either a K5 or K33 we could not avoid. So that is our contradiction. Remember, we assumed that there is a nonplanar graph with no K5 or K33. From that, we might as well assume that there is a minimal such graph, a graph G that is nonplanar, has no K5 or K33, and such that all of its subgraphs, and in general all graphs with fewer edges, are either planar or have a K5 or K33. We've then investigated some important properties that G must have such that it is 3 connected, which allowed us to deduce that it has this configuration, with an edge in a cycle going around the ends of the edge. We then investigated how the graph must connect within and outside of the cycle using our knowledge that G is 3 connected and minimal nonplanar. We then used casework to show that any valid configuration must either have a hidden K5 or K33, which was our contradiction. So we have now proved Kuratowski's theorem. We've shown that a graph is planar if and only if it contains no K5 or K33 subdivision, which is a very powerful, useful, and not so obvious fact. Good job! This proof is adapted from this proof by Yifan Zhu and this proof from Mary Radcliffe. They are very nice papers with very nice explanations of the proof and some additional maths I did not cover in this video. Most of all, I would like to thank Grant and everyone else at the Summer Math Expedition for giving people like me this chance to share their love of math with others. Thanks for watching!